Welcome to an introduction to the midpoint rule for numerical integration. You were first introduced to left and right Riemann sums when you first began the topic of definite integrals. Recall that the formal definition of left and right Riemann sums is that we suppose a function f of x is defined on a closed interval from a to b, which is divided into n subintervals of equal length, which is delta x equal to b minus a divided by n. Then the sum from I equals 1 to n of f of x sub I star times delta x is first a left Riemann sum if x sub k star is the left endpoint of the closed interval x sub k minus 1 to x sub k, and second a right Riemann sum if x sub k star is the right endpoint of the closed interval x sub k minus 1 to x sub k. As with many formal mathematical definition, it is easier to see an example. The following is the graph of the function x squared plus 1. Let's first look at an example of the Riemann sum if we use left endpoints. The green rectangles are generated using the left endpoints of the subintervals. The right rectangles are generated using the right endpoints of the subinterval. Now, another way we can generate rectangles is using the midpoint of the subintervals. The gray rectangles are generated using the midpoints of each subinterval. As you've seen before, the larger the number of subintervals, the closer the approximation is to the actual area under the curve between the two values. So the midpoint rule is very similar to what you've seen before with Riemann sum. Assume that the function f of x is continuous on the closed interval from a to b. If the interval is divided into n subinterval, each of length delta x equals to b minus a divided by n, and x sub I is the midpoint of the ith subinterval, then the midpoint Riemann approximation is given by m sub n equals the sum from I equals to 1 to n of f of x sub I times delta x. And the limit as n approaches infinity of m sub n is equal to the definite integral from a to b of f of x dx. So the midpoint rule is very similar. Let's look at an example. Use the midpoint rule with n equals to 4 to approximate the definite integral from 1 to 5 of 1 divided by x dx. First, the width of each subinterval is delta x equals to 5 minus 1 divided by 4, which is equal to 4 divided by 4, which is equal to 1. You next find the midpoint of each subinterval. It is not that bad this time because the subinterval is from 1 to 2, the second from 2 to 3, the third from 3 to 4, and the last from 4 to 5. So the midpoint of each subinterval are x sub 1 equal to 3 halves, x sub 2 equals to 5 halves, x sub 3 equals to 7 halves, and x sub 4 equals to 9 halves. The next thing to do is to find the height of each rectangle by plugging in each midpoint into the function. The value of the functions at each endpoint are f of x sub 1 equals to 2/3, f of x sub 2 equals to 2/5, f of x sub 3 equals to 2/7, f of x sub 4 equals to 2/9. The area of each rectangle is the height times the width, which would be the value of the function at the midpoint times the width of the subinterval. So the midpoint approximation with 4 subintervals is equal to 2/3 times 1 plus 2/5 times 1 plus 2/7 times 1 plus 2/9 times 1, which is equal to 496 divided by 315, which is approximately 1.574603. Now, using the techniques of integration you have already learned, the actual value of the definite integral equals to the natural log of 5, which is about 1.609437. If we had used a larger number of subintervals, then our approximation would have been even closer. Later, you will learn a formula for the error bound for the midpoint rule.